Okay, so you guys, everybody sees this reversible reactions lab. Yeah. Okay. So as you can see, there are a couple of things. Let me just explain what's what. This tiny thing that says 0K, it's not OK. It's saying 0K. That's the thermometer, which measures the temperature. On top, you see that there are two things. There are really tiny A and a tiny B, and there are two arrows. That's basically the equilibrium reaction. Yeah, that these double-headed arrows. You guys know what that means, right? We've done this in class. Yes, that's some amount of B is being formed and some amount of A is being formed at the same time. So we're going to look at these things at a molecular level. So this is pretty interesting. You see these levels on the left hand side and the right hand side. These are basically energy levels, yeah, actual energy levels. Remember we did in class that there was some middle point that's higher than both the energy levels of the reactants and the products. Yeah, the left hand side is the reactants, which is A, and the right hand side is the product B. I can arbitrarily call, this is just arbitrary, okay, that me calling A reactant and B product. Since it's equilibrium, I might as well do it the other way around. But at this point, let's call A the reactant and B the product. That's how we have designed this experiment. And you guys remember there was a middle point of high energy, that an energy barrier, so to speak, that had to be overcome to form products, or even to come backwards, yeah, to form reactants from products. Okay, cool. Just a bit of a revision. On the right hand side, you see that there is a temperature control. It seems like there's another thing called molecules in chamber. At this point, it's 0 and 0. I'll tell you how that works. Yeah. So an added thing called heat control at the bottom. Yeah, I can increase heat, reduce heat. Yeah, that's that's fire and that's ice. So I'm just going to keep it at 0 at this point. Nothing happened because it's paused. Okay. There's no molecule, so there's no heat. I add heat and there are no molecules, nothing's going to happen. Is that clear? The reason why the temperature didn't rise, because there's nothing in there. There are no particles of air or any gas. So if I'm adding heat to nothing, it's like heating vacuum. So the temperature will not rise. Is that okay? Does that make sense? Okay, cool, great. So let's get started. Let's set a few things. I'm going to set this energy level to say 22. Okay, that's how we've designed this lab. That's 21, 22 approximately. This energy level to 15. Hey, I can't be approximate. I have to be absolutely sure, because otherwise some things will change. One moment. This is 21. Is this 21 or is this 22? Can you guys tell? Yeah, you guys see that the left hand side is 22 or it's 21? Okay, excellent. Thanks for pointing that. Yeah, you are correct. Yeah, now we are at 22. Okay, 22 and 15. Hey, no. 1, 2. I think I've gone to 23 now. Okay, yeah, alright, great. Now we are set. So this lab would, yeah, it's fine, I realize, it's fine. So this lab will test your patience, because equilibrium takes time to set up. Remember, in the idea of equilibrium, this is very important, yeah? The idea of equilibrium does not care about how long it takes to get there, okay? You only care about particular points in the reaction, like, you'll know what I'm talking about very soon, okay? Do you guys follow that? It doesn't matter. So that's why we let enough time to pass. What we're going to do is we're going to change a few parameters, and we're going to let enough time to pass so that equilibrium is maintained. What is equilibrium? Macroscopically, the concentrations do not change. Is that okay? Just a bit of a recap of what equilibrium is, what we expect to see and all of that. Is that clear? Okay, excellent, cool. So, I'm going to increase the number of particles of A to 100. What do you think is going to happen? Yeah, left hand side, this is going to become 100. What do you think is going to happen? Couple of things will happen. I'll accept all answers. Just tell me what comes to mind. If I put in 100 particles there, what's going to happen? Look at all the controls that are there, all the things that can change. Inputs, guys. Are you guys typing? Don't see any response. Are you guys there? So what's going to happen? Don't sleep. Guys, why is nobody typing? What's going on? Everybody can hear me? I see only Anika saying yes. What about the rest of you guys? Can you guys hear me? Okay. There's viewer 8 and there's Anika. What about the rest of you? There are 4 of you in class at this point. Yeah, please respond. Okay, there are 3 of you. I see somebody left. But the point is, why aren't you guys saying anything? Come on, this is interactive, right? It's supposed to be interactive anyway. So tell me, what's going to happen if I add 100 particles of A? Not that difficult. Just give me some input. What do you think is going to happen? Okay, fine. Why nothing, boss? Okay, temperature rises. Yes, sure. Temperature will rise. Okay, I give that to you. But won't the reaction also happen? I have a reaction where A becomes B. Yeah, B is formed. Right? Do you guys see that? That both of those things will happen. Temperature will rise because it is at 0 Kelvin. It cannot go down. It has to rise. Is that clear? Very good observation. That's why I told you, just look around. There's nothing extra. You know, everything is on this simulation itself. Okay, good stuff. So let's see. Let's see how that works out. One moment. I press enter on the wrong keyboard. Yeah, there you go. Look at that. Right away, temperature shot up. A lot of things happening. The pale greenish thing is A. The pale reddish thing is B. Now you can see that there are molecules or these balls changing color, right? That changing color is basically means that they are forming product or reactant. That is also seen by the size of the A and the B on the top. You see that the size of B is increasing, yeah? Do you see that? And the size of A, the font, is reducing. That means to say that the concentrations are changing. How do you know? Look at the bottom right part, yeah? Bottom right thing is bottom right and bottom left. 40 and 60, yeah? You see those numbers? Yes? So that's the actual reaction happening. So we're going to wait for some time until equilibrium is established. What do I mean by equilibrium? When the concentrations are more or less same. Yeah, we will take averages. Like right now, okay, let's see if it has already reached equilibrium. Okay, I will take 5, I will read out 5 numbers. Okay, 5 sets of numbers. Please note them down. Do you guys have a pen and a paper with you? Everybody has a pen and paper? Okay, I'm going to give you 5 sets of numbers. Okay, Anika, get your stationery. So what I'm going to do is I'm going to give you 5 sets of numbers. Each set of numbers would be first A and B. I want you to give me the total average of A and the total average of B. Okay? If it is close to the numbers that I'm shouting out, then its equilibrium is reached. Clear? So I'm going to start in 3, 2, 1. 34, 66, 36, 64, 40, 60, 36, 64, 35, 65, and 33, 67. Okay, got it? What was the average of that? Just add up all the A's, divide by 5, add up all the B's, divide by 5. What is the average? Okay, and what is B? Sure. We have enough time. Hey, not this much time. You just have to add 5 numbers and divide by 5, guys. Come on. I'm going to do the exercise once again because it seemed like what Kirti said A, right? A 35.67. It's clearly gone lesser than that. Yeah? You see that all the numbers I get right now are lesser than that. Okay? So I'm going to repeat this exercise. Let's do this with a new set of numbers. Are you guys ready for that? Clearly that was not equilibrium because right now it is reducing and it's changing a little bit more. Okay? Hold on. I'm going to pause this and I'm going to take down readings. Okay. Again, 35.65. 32.68. 34.66. 37.63 and 31.69. Did you guys get that? Averages, please, of A and B quickly. I mean, if you get A, you obviously get B because 100. Hey, it can't be 56, guys. Anika, all numbers were in the late 60s for B. Okay, 33.8. Okay, I take that because 2 people are giving me 33.8, so I take that answer. Cool. So 33.8, approximately 34, and on the other side you have 66, right? Okay, so that's fine. Yeah, but be careful. But we're going to do the exercise enough number of times today, so you'll get good at averaging if nothing else by the end of this class. Okay, so 66.2. We'll run it off to 34 and 66, okay? Because, well, they're molecules, the actual particles. So can you guys now calculate the equilibrium constant? You guys know how to do this, right? You guys know how to calculate the equilibrium constant? Yes or no? Viewer 8 says 8. Yes, I'm sorry, I don't know who viewer 8 is. But yeah. I think it's Mayank. Okay, Mayank, cool. Please go ahead and calculate the equilibrium constant. It's simply the number of molecules of B by the number of molecules of A. Remember, it's not what I have paused at. It's the number that you guys have got, yeah? We need to take averages. So it will be 66 by 34. Okay? That's approximately 2. Correct? Yeah, 1.94-ish. Okay, cool. Let's take it to be 2. Okay? Let's take it to be 2. Just for, because we are doing labs here, we're just trying to figure out something very interesting. Now, remember what I told you guys about equilibrium constant? It does not change irrespective of the concentration. If the temperature is more or less the same, the equilibrium constant does not change. Do you guys remember that? Yeah? Let's see if that works out. I'm going to hit reset. I'm going to add now, say, 50 particles of A. Okay? And run the same experiment. Let the same experiment run out. I'm going to hit play now. There you go. We'll wait for some time, maybe 2-3 minutes for the same equilibrium to establish. And let's see if that happens. Okay? Now notice, we can predict for this reaction right away that it goes in the forward direction. Can you guys explain why that is? While this is going on, let me ask you a few questions. Why am I okay in saying that with the expression of K that we've just found, yeah, we got K to be around 2. So how can I say for sure when I'm adding 50 particles and there are 0 particles of B that there is definitely going to go, it's definitely going to go in the rightward direction? How can I say that? Any ideas? Kirti, is that a chess move? I did not follow what that was. Guys, can you do this or not? Can you guys tell me why I can say for sure that A forms B? No. It has to do with the equal. Remember this idea of Q. The reaction quotient Q, which is the ratio of products to reactants at any given point in time. It has to do with any given point in time. It doesn't care about equilibrium. It talks about time. So at the starting point, the reaction coefficient is what? What is the value of reaction coefficient? I told you it's the concentration of B by the concentration of A. So at the starting point, where there are 50 molecules of A and no molecules of B, what is the reaction coefficient? Exactly, it's 0. Since the reaction coefficient is lesser than the equilibrium constant, the reaction goes in the forward direction. If the reaction coefficient was greater than the equilibrium constant, then the reverse reaction would take place. Exactly. The reaction coefficient moves in such a direction to be equal to K. When Q is equal to K, at that point, equilibrium is reached. Yeah, all this is done in class, but I'm guessing it's been a while since we did this, which is maybe why you guys don't remember this. Is this okay? Okay, cool. So, while we did that, I think equilibrium has been established over here. Let's see. I pause. It's 18 and 32. Note this down, please. Numbers, note them down. Yeah? Okay. 1832, 1733, 1832, again 1733, 1634. Average, please. You can find out average of any one, yeah, because total particles is 50. 37.2. Okay. Okay, yeah, 23 and 37. Okay. So what is the ratio of 23 by 37? Hey, how can it be 23 and 37? It's 13, boss. And whoa, how can it be 37? Hey, guys, math. What are you guys doing? I don't remember calling out any number at any point in time. I did not call out 37. Yeah, I think that's more reasonable. Rohan, that's a reasonable answer. Come on, guys. This is adding 5 numbers, dividing it by 5. Please do this carefully. There's no hurry. I told you, you have enough time. Give me correct answers. That's more important. 17.2. How are you guys getting different answers? Okay, cool. Let's take 17. Two of you agree? 17 and 30. Yeah, okay, pakka. Okay, cool. 17 and 33. All right. What's the ratio? 33 by 17. What's the ratio? Remember, if I take concentration ratios at equilibrium, then that gives me the K value. If I take concentrations at any other point in time, it gives me Q value. 1.94ish again. So yeah, approximately again it's 2. Right? So we just verified that two things. Equilibrium constant remains the same and also nearly the same. Yeah, I'll tell you why it's not the same later on. We'll discuss it at the end of the class why we get some variations. Because clearly you see that there are some particles, it's dynamic, right? So things are changing. It's not constant at that 17 and 37 point. It keeps changing, right? Yeah, that's why we take average of 5 different numbers. That makes sense to you guys? Why I took 5 snapshots and gave you 5 numbers. So that's really important in any experiment you run. If you choose to do science, whatever you do, you need to have multiple numbers and average it out. What we did was a really easy, straightforward, like, just adding. There are many other more accurate averages that can be taken. If you take up science after 11th and 12th, you will learn about them. But even 11th, 12th, you will realize that when you do lab experiments, you must take many readings and you must take an average of them. Okay? All right. So, I see that more people have joined in class. I'm not sure who all are there. Wait one moment. Okay, I see Sanjana, viewer 8 and viewer 10. Viewer 8, I remember, was Rohan, and viewer 10 is Asmita from the class. Okay, all right, cool. Okay, great, cool. So yeah, you guys will catch up easily. This is a very straightforward lab. So Remember, I told you what the idea of Q was. Are you guys clear on these 2 points, Q and K? Q is the ratio of concentrations raised to a stoichiometric power. That happens to be, stoichiometric powers happen to be 1. Okay, that's why we are not worried about that. You guys remember this? Something of what was taught to you in class? Yes? Somewhat. Come on, you absolutely must go back and read the notes. Otherwise, this quiz may be like Greek and Latin to you, yeah, after this class. So please read up on the concept class notes that are pertaining to this quiz. That will make life easier. You can attempt the quiz right away, but it may demoralize you, which is why I'm saying please look at the notes before you answer these quizzes. Okay, cool. So we figured out that equilibrium constant remains the same, and Q tries to approach the equilibrium constant. Agreed? So this is interesting. Q tries to approach the equilibrium constant from any direction. We have just seen left to right. Let's see. I'm going to reset this entire thing. I'm going to pause this simulation. What I'm going to do now, I'm going to add some amount of A and some amount of B. I don't know which way the reaction would go. Actually, I do know which way the reaction would go. Can you guys tell me? If I add 40 molecules of A and 35 molecules of B, what's going to happen? Which direction is the reaction going to go towards? Remember, the K value was approximately 2. So which direction is the reaction going to go in? Okay, let's see. Let's see. Your logic, I presume, is because Q is less than K, so it should go forward. Okay, that sounds good. Let's see. There you go, there you go. I'm going to hit play now. So yeah, right away, 40 has definitely reduced. Yeah, it's become 24 already, which means yes, you guys are absolutely correct. It did move in the forward direction, which is good stuff. Now, can you guys calculate B is getting bigger? Yeah, exactly. I told you guys, right, that yeah, B is getting bigger. Okay, that's an easy way of saying. Cool, good stuff. Can you guys calculate the concentration at equilibrium? Yeah, while this happens, can you guys do that numerically? If I take the number of particles at equilibrium A to be X, I will obviously have 75 minus X particles of B. I'm doing this verbally because it's straightforward. If you want me to go back to class and write this down, let me know. Do you guys want that? This is really straightforward. Do you want to pause this and go back to class? Or would you do this right here? What about the rest of you? Kirti says is okay. Anika is okay with this as well. Can I have everybody interact and tell me? Here. Mayank, Rohan. Okay, cool. Alright, cool. Okay, unanimous then. So, if I have X number of particles of A, then clearly I have 75 minus X particles of B at equilibrium. Is that alright? So, using this, can you solve for the equilibrium concentration? 75 minus X by X, which is the concentration of B by concentration of A, should be equal to 2. Right? We figured out the equilibrium constant was 2 from the earlier 2 cases. Using this, can you solve for X? Can you solve for X? Give me the value of X. Okay, that was neat and quick. X is 25. So, this is really interesting because now I know when to stop the reaction or when equilibrium has reached. Right? So, you know that if I have data for a particular reaction and if I have the same products and same reactants and also at the same temperature at any other country or wherever I go, it will follow the same rate law, right? So you know at what concentration equilibrium is reached, right? So I can stop the reaction at that point or whatever. If I need, there are some things that you need to do. There are many reactions where you need to reach equilibrium and then you do some other stuff to it. Yeah, you will learn more about this in organic chemistry. But at this point, so when the reaction of A, the concentration of A is approximately 25, around 25, then we know that equilibrium is reached. Do you guys agree? Does everybody agree with that? Okay, cool. So let's wait for a couple of minutes for that to happen. In the meantime, if you guys have any questions, please ask away. Any questions, guys? The guys who joined late, do you guys have any questions? I've discussed what is Q, I've discussed what is K, shown both those things practically. So the guys who came a little bit later, if you guys have any questions, please ask away now on the lab chat itself. Okay. What have you forgotten? Because, well, equilibrium is taking a lot of time to set up, so I can actually teach you this stuff right now. What have you forgotten? Tell me. Like Q and K. You vaguely remember some formula. K is equilibrium constant, which is basically the ratio of concentrations at equilibrium, as simple as that. What is equilibrium? It's dynamic equilibrium. Yeah, like this. Macroscopically, it looks like the concentrations are same, but microscopically, reactions keep happening. So this is a microscopic view, and so to speak, this is like midway between micro and macro, okay? Because you see that there are a number of particles. In an actual reaction, you have like billions and billions of particles. Here, I'm just taking 100 particles. So it's in between micro and macro state, okay? Which is why we are taking averages. About entropy, that is not possible at this point. I'm trying to explain what we are doing in this lab. Entropy just says that entropy was okay. You want a revision of entropy? Huh. Well, since this is the last chem class, okay. Well, if you guys want a revision on entropy like an entire class, you'll have to email Deepak about that. But if you have particular doubts in entropy, then feel free to ask on the forum, and I'll answer right away. Okay. I was talking about this particular setup in this reaction that we have here. Any doubts here? Q and do you understand what K was? The exact formula for, yeah, this is the last chemistry class, as far as I know. Did you guys figure out the formula for K? Did you guys understand that? I'll tell you what Q is. Well, you can join us next year for more chemistry classes and physics and math. Anyway, so equilibrium constant, the formula has some other components to it, yeah? It's the concentration raised to its stoichiometric coefficient. All that you can go through the notes. But in this reaction, since the stoichiometric coefficients are 1, it's cool. Okay? Is that understood? The idea of K? Okay, cool. So equilibrium IC has been established. I saw 25 and 50, but this guy decides to have changed up again. But you guys get the picture, right? It should be approximately 25 and 50. Yeah? Okay. If you do actually take averages 5 times, it will give you the same value. Okay. So now I'm going to go ahead and let's see with the initial example of total particles being 100. Remember when I took the particles of A to be 100, it's as good as saying that if I take any particles of A and B, their sum being 100, then at equilibrium, there will always be around 34 particles of A and around 66 particles of B. Do you guys agree with that? That's what the idea of K means, right? That's very important. If you have the same particles, same number of particles, then irrespective of which direction you approach equilibrium from, the equilibrium concentrations are always going to be the same. This is extremely important. Do you guys understand this? Okay, good stuff. So I'm going to do something cheap here. Since I already know the equilibrium concentration to be whatchamacallit, I know the equilibrium concentration to be 64 and 37. 34 and 66. I'm going to do exactly that. I'm going to reset everything. I'm going to add exactly 34 particles here, exactly 66 particles here. And let's see if there's an equilibrium position. Yeah. I'm going to hit play now. So while that happens, not much going to happen because I added things at the equilibrium concentration itself. Hopefully, we'll come back to that situation very soon. So in the meantime, I will explain Q. Q is the reaction quotient. Reaction quotient. What that means is it tells you the extent of reaction. Okay. I have arbitrarily chosen that A to B is forward and B to A is reverse. It's not. So wait, it's going to come back. That's the point. It's dynamic equilibrium. So that will happen, and eventually it will always be 33 and approximately that ratio. Yeah, let's wait. That's what I'm saying. You guys are going to have to be extremely patient with this lab, which is why this lab has tiny experiments, but they take time. They actually take time to do, as you can see. So Q, you guys understand Q? Q is basically the reaction quotient, and it tells you the extent of the reaction. How? The same expression as K, but instead of the equilibrium concentrations, I take concentrations at any other random point in time. Is that clear? Any other doubts in what we are doing today? You have understood Q, you have understood K. Okay, great. Anybody else? Do you guys have any other doubts? Okay, excellent. So, as you can see, this is already reached equilibrium because I cheaply did add the equilibrium concentrations. What are A and B? That's a very good question. A and B are random things like, I can't think of any reaction that actually has 1-to-1, but it's basically, they're basically chemicals. Okay? Alright? Great. Because any reaction that I give you, a chemical reaction, would form more products. It will not be a chemical reaction which is giving A to B. You understand that, right? It could be a physical reaction. If you've done organic chemistry, isomerism, right? One isomer can, or not isomer, tautomerism specifically. So that could happen. But this is just an easy representation so that you don't have to do scary calculations, math calculations. Yeah, that's the reason behind this. So you see that is obviously at equilibrium. Now I'm going to pause this and I'm going to remove 25 particles. What do you think is going to happen now when I remove 25 particles? This would be the same effect. Okay, good stuff. I did not say 25 particles of what? I was going to say 25 particles of A, but it seemed like you read my mind and gave me the answer right away. So yes, it does go backwards because I've removed some concentration of A. Yes? But to what extent does it go backwards? Can you guys tell me this? This is the same case as adding 40 and 35 because the total number of particles is still 75. So like you guys calculated, the expected concentration of A will be 25 and of B will be around 50. Agreed? Yes? Let's see. Let's verify this. Okay, sure, Rohan, sure. So let me repeat what we've done so far. Initially, I took 100 particles of A, none of B, started, established equilibrium. So then I figured out that for 100 particles of the total system, I have this equilibrium. Yeah, approximately 33 for 67 or 34 66. Okay, is that okay? That was what we did initially. Then I halved the reaction of, halved the concentration of A. I put in 50 molecules instead of 100. Even after that, I figured out that K was the same, which means that equilibrium constant does not depend on concentrations. Clear? Then I took 40 particles of A, 35 particles of B. Again, I got the same equilibrium concentration, which again means that irrespective of what direction I start from, the equilibrium reach is always going to be the same. Okay? And we figured out that for 75 particles, there would be 25 of A and 50 of B. Agreed? So we jumped ahead from having total particles being only of A to some random particles of A and B, which being 40 and 35 in the case of 75, and 66 and 34 in the case of A and B, when the total particles are 100. Agreed? So now we are talking about total number of particles. So if you have the same total number of particles in the system, the equilibrium concentration will also be exactly the same. That's all I'm trying to say. So when I have 100 particles now and A, if I remove 25 particles from A, that means the total number of particles now becomes 75. It will form the same equilibrium as earlier, which would be 25 of A and 50 of B. This is a direct consequence of Le Chatelier's principle. This is agreed. Remember that? LCP and all that, we did that in class. Okay, good stuff. 31 minus 25 is 8. Yes? Okay. So, what is the reaction quotient for this reaction? You guys said backwards, intuitively, using LCP and all that. Can you tell me what the value of Q is? More than K. Suffices. It's more than K. And guys, 69 divided by 8 is close to 9. How the hell is it 6? Please be careful about these things. A safer answer would be, as Rohan said, more than K. Oh, 31 minus 25 is 6. Okay, great. Yeah, that makes sense. Thank you so much. You answering that question. Thank you. I don't know how I did 8. Yeah, eat my own medicine. I should be better at calculations than that. Thank you. Okay, now I'm going to resume this reaction, okay? Cool? So, yeah, since Q is greater than K, reaction goes backwards, as you guys predicted. Just one moment. Now, if instead of subtracting 25, I added 25 particles, what do you think would have happened? (25) to A, same. I'm talking only about A at this point. I'm only disturbing A. Which direction was the reaction? Not right now. I'm talking about the initial position. Now I've removed, now assume that there were still 100 particles. To that, if I added 25 of A, what would happen? Equilibrium was established. Yeah, exactly, forward. Let's see. Let me pause this. And let me add 50 now. Why 50? Because I removed 25, I want to add 25. So I'm accounting for the removed 25 and also the added 25. So that would be 66. Agreed? Is that alright? Okay. I hit play. Now, the deal is that the system is basically trying to oppose the disturbance caused. I added A, it wants to reduce the quantity of A. If I remove B, it wants to increase the quantity of A. Does that make sense? Okay. Now this is basically the Le Chatelier's principle. Okay. So we can also do this. Say that was qualitatively figured that out. Quantitatively as well, we can do this using the expression for K. Right? How? Not K, I'm sorry, the expression for Q. At that point, the value of Q would be, say, 68 divided by 32 plus 25. Can you guys do that? What would that value be? At the earlier equilibrium that was established, it was approximately 68, yeah? Particles of B were 68, particles of A were 32. I add 25 to that, so that becomes 37. Yes? So Q Yeah, sorry, 57. Yeah, 57. So Q clearly now is lesser than 2. Right? Because the concentration of B was approximately 68. Yeah, it's less than 2, definitely less than 2. That means that equilibrium shifts forward, which is what we see has happened. Right? So that's it. That was just a bit of a calculation. So we can do this two ways. One is using the Le Chatelier's principle, and then you can confirm that using the principle of equilibrium. Cool? So let's wait. Play the waiting game. And while this happens, I will explain to you why there's a bit of a, it's not exactly 2, or it's a bit up and down. That's mainly because, see, equilibrium constant, if you guys remember from our classes, K is dependent on temperature. Yes? And as you can see, the temperature is mental. It's moving up and down. It's not at a constant temperature. You see there's a difference of 20 or 30 Kelvin even. Went to 200, went to 170, 160. Yeah? So temperature is fluctuating a lot. Right? Which is why the number of particles change. Why is the temperature fluctuating? Because the products and the reactants, right? That also keeps changing. The number of products and number of reactants. Okay? So, I'm not going to wait for the equilibrium to be established. You guys have understood the idea behind it, right? Yeah? So, you can figure that out. You can do this in your free time. The point is that equilibrium constant depends on temperature. Now, in this case, the final, no, K is constant. This is a very crude example, which is why K, no, you get K to be constant, no? I took averages, right? This is the importance of taking averages. Remember, K was constant. But the reason why we took averages, the reason why the number of particles keeps changing, I was trying to justify that. Do you understand that now? Like, see, at this point now, it is reached equilibrium approximately, because the ratio is approximately 2:1. Right? You see that? Well, now it's changing, but approximately. Okay. So, this is very interesting. Yeah? Last part. You see that the energy of the products is lower than the energy of the reactants. You guys see that? I'm talking about the blue lines now. I'm not talking about the yellow thing in the middle. The blue lines. The final energy of the products, final energy of the reactants. Therefore, it seems like heat is produced in this reaction. Agreed? So, if I increase the heat added to the system, what do you think is going to happen? Think of heat as a part of the reaction. So I'm writing heat. If I were to write this reaction, I would write A gives B plus heat. No, be careful. Listen to me carefully. Listen to me carefully. So heat is like a product of the reaction. So if I increase heat, clearly the reaction goes backwards, because the disturbance I've caused is I've increased heat. It would want to decrease heat. The only way it can decrease heat is to go backwards. Does that make sense? This is an example of an exothermic reaction, because the final energy of the products is lower than the initial energy of the reactants, which means that there's negative energy. Negative energy means heat is released. Now, to write that in this reaction, I would write it to be B plus heat. Is that clear? Is that idea okay? Extremely important. Very cool idea. Let me pause this and see if that really works out. Paused. Add a lot of heat. Okay, no, I can't do that. Let me keep it playing. I'm going to keep it. Wait a moment. There you go. Heat. Yeah, why is that surprising that there's no lag? Is that a happy comment or is that a surprised comment? I don't get it. Okay. There usually is. Okay. So, yeah, here, now when I did that, something a little messed up happened. Particle escaped the prison and surprised. Okay, cool. Yes? Now, the important thing to see here is that the value of K has reduced. Right? Which means that the number of particles of A have relatively increased. Does that make sense? That's what we predicted. Reaction goes backwards. Cool? That's it. That was the idea behind this reaction. Yeah, ideally this should have been a completely closed box and the particles shouldn't have ran out like that. But, well, there are limitations to free simulations. Okay, so that was it for this lab. I'm going to pause this. I'm going to stop the recording over here. You can come back to class.